Oh my god. I really forgot. Yeah. Two-person. Perfect information. Games. So what it means is that we have two people who are playing with each other, and perfect information means that everyone knows what were the moves of the game. Like, you know, in some games, like your opponent makes move, but you don't know what his move was. But in this game, you will always see what was his or her move. Okay. Then another thing, what is very important for us, no randomness at all. That means no dices. So like every player should be able to make moves that he or she thinks are needed. Okay. Also, they have to go in turns, like they cannot go simultaneously. Okay, cannot make simultaneous, sorry, I don't know how to put it with simultaneous moves. That means they go one by one. And then another important thing is that there is always a winner. So this kind of games are called zero-sum games. Because that means somebody loses, somebody wins, and then in total that's zero, right? Like there can be no draws in the game. So let's take any game that's like very popular. You can take chess, checkers, or even Go. And so if we take chess, we can just modify it a bit so that you make it so chess would always end. There will be never a draw, and there will always be a final game. So like in chess, we have a rule that if the same position of like occurs 3 times in the game with the same player, the game stops, right? Okay, so basically, knowing this, we were able to prove that chess is a finite game. Why? Because there is like a maximum amount of moves you can do in the game, and after that amount of moves, we just start repeating positions. And because of our rule, you cannot repeat positions more than 3 times, you just stop the game. So if you are curious how to do that, I have notes that I sent to WeChat, and you can just check them out. But basically, we prove that chess is a finite game. And also, we modify chess so that if you ever have a draw, we just say, for example, the first player wins. Or you can say, like, the most beautiful player in the game wins, or whatever you want, right? So why do we need it? So we always have a winner. And then, after we modified our games, what we did is that we saw a graph. So imagine that each configuration of figures in chess on the board in time are different positions in the graph, like different vertices. And so there was some starting position, you know, like all chess start with a specific position, right? That would be our first vertex. And from here, the first player is able to do some moves to, say, the 3 vertices. I mean, maybe there are like 10 available moves, right? And then after that, the second player is doing some moves according to the game, and etc., etc. So basically, because the game is finite, this graph someday will just end. Okay? By the way, this graph is called a tree graph. I really don't like this marker. You think I should change it, or you're fine with it? Because I really don't like it. Okay, so that's a tree graph, and it is a call it a leaf. You know, just like leaves on trees. That's like an ending of the tree. And then we have like different of those leaves. And so basically, because we have rule that somebody always wins, in each of this leaf, one of the players won. Like maybe this was the leaf when the first player won, and let's just mark them like that. And if the second player wins, we just mark the leaf like that. And maybe this and this are also winning for this second player, and then this vertex is winning for the first player, right? And so what we're able to do is look at different cases. So imagine that there was a winning situation for the first player, right? And the move to that situation was done by the first player, right? Okay? Are you good at this? Okay. So basically that means that this position was actually also a winning position for the first player. Why? Because even if there were different kind of moves a first player could have done, if he has at least one position to choose where he can win, I mean, why would not you just go there, right? So that means that this position is also good for the first player, right? Okay, so imagine another situation when it is a winning move for the first player, and then the second player has his or her turn. Hey, okay, so that basically means that we have two cases here. Either second player just doesn't have any choice. Like imagine that all of these positions are actually winning only for the first player. That means that this position is also winning only for the first player. Why? Because second player just doesn't get a choice. Like anywhere he or she goes, like he or she just loses, right? That's also a vertex that would be winning for the first player. And if the second player actually had a choice to go to the vertex where he or she wins, it means that's a winning vertex for the second player, right? And we just go through such a logic from the end of the tree. So basically what it means is that if we know that this vertex is the last vertex, and if this vertex the first player wins, we see who did the move here, and if there were other possible moves, and blah, 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 then we just color the graph according to this logic, and we go up, up, and up. And at some point, we'll be able to know this vertex was a winning position for the first player, for the second player. Okay, so let me just give you a pause here so you'll be able to understand that this is actually pretty cool. Why? Because if you think about it, we have tons of games which are played by two people, and when you know how, like who made which move, they are not random and you don't go simultaneously, right? So we have tons of those games, especially chess or like checkers or whatever. And we were just able to prove that if those games are finite, and they are, because usually humans tend to make rules that would make the game finish, otherwise what is the purpose of the game? You'll be able to always find somebody who actually has a winning strategy. Like chess has a winning strategy for one player. Like if you'll be able to draw this graph for chess, there would be just no meaning in playing chess anymore, just because there already a winning strategy for somebody, right? It just makes most of the games meaningless. Like, isn't that cool? Right? Okay, so the thing here is basically it's just hard for us to draw the graph. That's why we still didn't find a winning strategy. And just to clarify, how much of you understand when I say winning strategy? Like, what do I mean by a word winning strategy? Okay, great. People who are going to the first lecture. Okay, let's just explain briefly. Winning strategy is basically an algorithm for anyone to win the game. Like it always brings you to the winning position. Like if, for imagine you have a computer and you just type an algorithm. If your opponent does this, you should do this. So this algorithm should be very precise. Like, because computer doesn't understand how to play, you just have to make like strict rules of when to play. And with this graph, we just show you are able to actually write such an algorithm if you have this graph. Okay, so what we just did was actually a weak statement of the theorem. So basically, it's a Gale-Stewart it's a weaker statement of Gale-Stewart theorem that says for any finite game, there is always a winning strategy for somebody. Okay, great. That's what we did in the first lecture. And today, what we're gonna do is we're gonna go and look at the games of infinite length. Why? Because why not? They're fun, right? Okay, so a lot of people maybe can ask me a question, why should we study infinite games? I mean, this is a very cool topic, I believe, because I mean, who doesn't like games, who doesn't like infinity? But the thing is that it's actually a very good tool for solving a lot of cool problems in set theory. And they are basically very powerful facts. So today, what we're gonna do is show you like a bunch of cool facts. And I'm just gonna like say it right now. Like, it is okay. It is totally okay if you don't understand every detail in the proofs that I say. Because I mean, math lectures are usually hard. Like, and it's okay if you don't get all the details right now. I'll post my notes. But it's important for me to get like intuitive understanding of the concepts I'm talking about, because I think they're pretty cool and like mind-blowing. Okay, so let me first talk about axioms and set theory. So in our set theory, we have specific axioms that people said, okay, we'll just believe in that statements. Because we cannot prove them, we'll just derive all the proof from the statements, right? And there is a thing called axiom of choice. So axiom of choice, it is an axiom that basically people didn't pay much attention to it. People didn't even know that's axiom until people just like started to notice that this thing actually leads to paradoxes. So what does axiom of choice tell us? It is actually a very intuitive thing. Imagine you have infinite amount of some sets, right? And you have some stuff inside. And the axiom of choice basically tells you that you are able to take one thing out of each of those infinite sets. Okay, and at this point, I guess it's already mind-blowing. Why do you even need an axiom? Because I mean, that's totally intuitive, right? Like, I mean, why can't I just like go and grab like one pen from each of your bags, right? I can do it in my life. Why can't I do that in set theory? And the problem here is that infinity doesn't always allow us to do stuff that finite sets allow us to do. And in infinity, our intuition just doesn't simply work. So that's the problem with it. And so basically, why is this axiom just so painful to use? Because it leads to paradoxes. I mean, there is a paradox called paradox of Banach-Tarski. Banach-Tarski is basically can be formulated like that. Imagine you have an orange, you cut it into finite amount of pieces, you rearrange those pieces, we got 2 oranges. Like, okay guys, like, who of you believe that I'd be able to do that in real life? Okay, great, no one, because I mean, you can't, right? I mean, the volumes cannot just like double and etc., etc. But like they were able to prove that, and that's a very valid proof. And the problem with the paradox is that those guys say that this paradox exists because of this thing. Because you cannot just simply allow to take one element from infinite amount of groups. There are cases when you are allowed to take those. Like if you have finite amount of sets, it is totally okay to take one stuff out of each set and you won't be punished for it. Okay, that's totally fine. Another case, when you can take one stuff from each of the infinite amount of sets, is if you'll be able to find an algorithm that helps you to distinguish each thing that you'll be able to find. For example, my algorithm would be, I want to take the minimum element from each of the sets. Okay, if I actually have a minimum in each of the sets, this algorithm works, and I don't need this axiom of choice. So I can just not use it. Why this is a problem? Because some of the sets are actually infinitely big, and if in my set I have number 0, minus 1, minus 2, minus 3, and etc., I never have a minimum, right? Okay, is that understandable now? Okay, good. So like, that's a problem. It's just hard to find an algorithm that would allow you to distinguish one element from each of the set and take them. So that's why some people use this axiom of choice, because it helps you to prove a lot of cool stuff, right? A lot of powerful theorems. But some mathematicians just don't use it, and they are able to prove some other stuff without it, right? But imagine how cool it was to be a mathematician who were like, oh my god, wait, so we were using this thing in all of our proofs before, and we never actually noticed that. And that means you have to go back to all your previous proofs and check if you have this little intuitive thing inside. And sometimes you would be able to escape it. Sometimes you'll be able to go in another way and still reach the same result without it. But sometimes you just cannot. And that's what's so hard about it. But today, what we're gonna do is we're gonna remind ourselves that we have actually topic infinite games. And we're gonna see following. Okay, we proved that for each finite game, there always a winning strategy. Okay? And so we really want the same result for infinite games. I mean, why wouldn't we have a winning strategy for everyone even if the game is infinite, right? I mean, that would be such a nice thing to have, right? I mean, why wouldn't you want this thing? The problem with it is that if you remember our proof with a graph that we had just right now, right? When we start with the bottom of the graph and we go up and we color stuff until we reach the first vertex, the problem with it is that in infinite games, you don't actually have the bottom of the graph. Oops, okay, we have a problem. What do we do when we have a problem? Let's make an axiom. I mean, that's not how we solve problems, guys, right? But like, just sometimes you do that. Okay, so we would make up an axiom called Axiom of Determinacy. And this is a very cool axiom, because what it tells you, it says for any game that we saw, like with those criteria that we talked about before, like it should be two-person game with perfect information, no randomness, blah, blah, blah. For any game with such criteria, you always have a winning strategy. Great. Okay. So if you just assume that this axiom is true, you will be able to prove a lot of powerful stuff. And what we're gonna prove today is that every set is Lebesgue measurable. countable, don't worry, and I'll tell that right now. So, first, what is a measure? Okay, maybe some of you ever ask yourself a question. So imagine you have an interval 0, 1. So its length is 1, right? Right. But what if you say, oops, I want to take a rational point out of the whole intervals, I want to take all points 1/2, 56, 58, whatever, right? All rational points, and just delete all other points. So what would their lengths be? Anybody have a guess?
What do you mean by their length?
That's a very good question. We're gonna define it later. But just I don't know, just your intuitive understanding of how much those points together would make up, in length. 0, great. That is a correct answer. I'm not gonna give a proof for it, but to give you an intuition, each point has a length 0, right? And you have small number of rational numbers if you compare with all possible points in the interval. And so you just add up to 0, right? But then you say, wait, but this interval is made of infinitely many points here, but it still gives us length 1. What's wrong here? It's just the infinite amount of rational numbers is just somehow less than the infinite amount of all points on the interval. And okay, at this point we came to a thing called cardinality. So cardinality is a fancy word, but what it basically means is size of an infinity. So you have natural numbers, and we usually say that they are countable. Countably many means infinitely many, but it also means that you can make a bijection with natural numbers. So if there is any set, and basically if there is any set, and to each point in this set, you can find a point in natural numbers, and backwards too, then this sets have a bijection between them, and this set is countable. Means that its size is kind of like the size of natural numbers. How many, there is infinitely many natural numbers, but you'll agree that there are less natural numbers than of all numbers, right? Okay, great. And then there is real numbers, and they have cardinality of continuum. It's just a fancy name. Basically, it means big infinity, small infinity. Okay, and there was a question, I guess it was you in the last lecture, who was asking, so where do rational numbers, what is their type of their infinity? And actually, we are able to prove that there are as many rational numbers as there are natural numbers, kind of. Their sizes and their infinities match. Yeah, and I actually promised I will bring a proof of that. And okay, so the proof goes like that. 1, 2, 3 minus 3. I actually guessed it's a proof on the last lecture, but I kind of didn't understand that it was a proof. Okay, 1, 2, 3, 4, blah, blah, blah. Okay, basically, the way it goes is like this. Some set is countable if you are able to take all its elements able to count all elements just like that, that means here it is a countable set. That means you can count it with natural numbers, right? I mean, the name just tells you that. So basically, we just have to come up with a fancy name of ordering our rational numbers. And the way we do it is just like that. We take this, and this would be our, I forgot how to call it. In fraction, we have the denominator, and what do you call it stuff? Okay, it's not at the top. Yeah, no native English speakers here. Great.
Numerate.
Huh?
Numerate.
Thank you so much. Because I don't know the Chinese name for it, and like, okay, so in my class, these are numerators, and these are denominators. And I just go with like this. And like, on the intersection of this table would be like 1 divided by 1, minus 1, 2, blah, 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 right? And here you would have 1/2, and etc. So basically, if I'm able to do this line, that means I'm able to just go around and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and etc. That means that I can count all rational numbers, and the proof is done. Okay, great. So that means rational numbers are countable. But you can actually prove that you cannot do the same stuff with real numbers. We're not going to do that today. Anyway, so basically, there was the background we needed if you didn't have it. So talking a bit again about measures. If all the rational numbers here make up length 0, then what length would all irrational numbers make up on this interval? Can it be 0? No. Why? Because if you see, like, you have rational numbers, irrational numbers, you add them up, you get the whole interval. Whole interval's length is 1. Rational numbers' length is 0. That means irrational numbers' length is 1. Good. We found the length of irrational numbers. So, okay, that is what measures intuitively are. And there are different ways to define measure. There are Jordan measures and Lebesgue measures. And today I'm just going to show you the definition of Lebesgue measure. Because, I mean, why not? And actually, the Lebesgue measure is kind of a good measure. People usually refer to it a lot. So I'm just going to write a very scary formula, and I'm going to explain it, okay? I mean, you can just try to decipher what this all means. If you are able to do that, that means you don't actually need it here anymore. I mean, you don't need it here anymore anyway if you study by yourself, but that would not be as fun. By the way, are you coming to Ryan's lecture about Fourier transforms? It probably would be next week. Such that the okay, so I wrote this scary formula, and let me just explain briefly what it means. So imagine we have some set E on an interval 0 to 1, why not 0 to 1? Like, these points are in the set E, these dots are in the set E, this interval in the set E, just, you know, some random combinations of points are in the set E. Okay? Okay. and we're gonna take infimum. Infimum basically means we're gonna take their smallest possible minimum. So we're gonna make them as close as you can to actual points of the set. We're gonna sum it all up, and this will be our measure. This is actually called outer Lebesgue measure. Okay, great. So we have this. What we also need, and I'll show you now why we need it. I kind of don't have enough board. Okay, let me just erase this. Okay, what we also need is inner Lebesgue measure, as you can guess. And it would be defined as A minus A. Okay, great. So we're just going to define inner Lebesgue measure using the outer Lebesgue measure. Why and how? Okay, so imagine A is just our whole interval, 0 to 1. Okay? We're going to take E complement. E complement means everything in the set A except for the set E. So like this is and this and this and this is lying in the complement of E. Okay? Good. So we're gonna take their measures. Like we're just gonna estimate all of their measures by this procedure as we did before. And we're just gonna take the whole measure of the whole interval and subtract it, and subtract the measure of all those complements out of it. And we'll have the inner Lebesgue measure of this. Is it intuitively understandable why this works? Okay, great. Clear? Okay, great. So why this and this are not the same things? Because here you're taking open intervals. And open intervals can sometimes be just a bit bigger than the interval itself. But in big sets, that would actually count. So like, it would actually be just a bit more than the actual measure of your set. And for some sets, it would not matter. But for some sets, it actually would. So, and what we do here is we just take the measure of the complement, but because it's open sets again, we actually are taking just a bit more, just a bit more than the complement, right? But when we're gonna subtract it, it's just gonna take a bit less of our original set E. So that's why it would be a bit less than the measure of E. So that's why we call it inner Lebesgue measure, because it's a bit smaller than the actual setting. And this is outer Lebesgue measure, because it's a bit bigger than the actual measure of E. Okay, now do you understand what I'm talking about here? Great. I mean, guys, you're doing a great job. Like, it took me like about half an hour staring at this in textbook, like to understand what it means. So, I mean, you're doing a very good job here. So what happens is that the set is called Lebesgue measurable if outer Lebesgue measure and inner Lebesgue measure are equal to each other. That means if our maximum or minimum are the same, that means we were able to actually meet the set. But if it's not, that means we were doing a very bad job at estimating what the measure of the set was. That means this measure was not doing a good job. It means the set is not Lebesgue measurable. Okay? Okay, that's just a definition. So basically, a lot of good sets are Lebesgue measurable. That was so good about this definition of Lebesgue of a measure, like that was made by Henry Lebesgue, is this because, I mean, a lot of good sets have a property of being able to be measured by this Lebesgue measure, and this gives us a lot of stuff we can work with. But there are still some very bad sets that we don't like because they're not Lebesgue measurable, because they're very awkward, because they jump as crazy, and it's very hard to like catch them in those intervals and actually measure them, okay? So we don't really like this set. And guess what we're gonna show today? We're gonna show that all of those very bad sets that we don't like because they're not Lebesgue measurable would not exist if we wouldn't have an axiom of choice. Isn't that cool? So, I mean, okay, no. We would prove that using axiom of determinacy, we can show that every set is Lebesgue measurable, right? Okay, so it's not because it is a bit because of axiom of choice that those sets exist, but that would not be a very correct statement. So, okay, I'm just gonna give you a little pause so you can ask me a question if you have any, and just do you catch like intuitively what I'm talking about? Like at least like some big picture of what's happening here. Okay,
Yeah,
that's great. I see some nodding. It's actually pretty cool. I hope this mic is right. Okay, great. So we talked about the Lebesgue measure, and now we're just gonna see an example of a set. This set is not Lebesgue measurable. Not Lebesgue measurable. I guess I just called non-Lebesgue measurable, but I'm not sure.
Excuse me, how to spell that? What measurable?
Sorry,
No.
wait.
No. How to spell the word before the word measurable?
Lebesgue?
Yeah, that's best.
Lebesgue.
Oh, shit.
Sorry, my handwriting is kind of sloppy. Okay, so we're gonna look at this set, and it would show us how axiom of choice leads to existence of those finally sets, and those finally sets are non-Lebesgue measurable. Okay, that's what we're gonna do now. How do we construct Finality sets? That's a very good question. Let's just take interval 0, 1. Yeah, you actually have to take 0, 1 all the time, because like, it's just so nice to work with 0, 1, right? Like, because like, I mean, you can do the same logical proof with like any interval you want, but like, why should you care? So yeah, so let's just throw out the point 1 out of here. Yeah, I'll show you why. So then we'll just say that any point P and Q are equivalent. You're gonna hear equivalent, that word a lot of times. I mean, for us it just mean that they would be in one group. They would lie in one group if P, Q lies in rational number. That means that their difference is a rational number. So say like anything like, say, oh I don't know, square root 2 plus 1/2 is P, and square root 2 plus 1/5 is Q. Their difference is just 1/5 minus 1/2, and that's a rational number, so they are lying in one group. Okay? Good. And well, rational minus rational less rational, blah blah, and then like irrational plus rational are irrational, we can arrive to a conclusion that if we're just gonna do this operation with all the possible points, like all the possible p and q in this interval, we are gonna arrive to different equivalent classes. Equivalent classes. For example, one of them would be just all rational numbers in the interval 0, 1. So like just all rational numbers, like their sum or their difference is rational. That's why they all would be in one group. Good? Okay. And then we'll have something like square 2 plus rational numbers. We're just going to write mod 1. Mod 1 would mean that, if you have 5, 2, we're going to take 5 out of there and write 0, 2. So it just takes your non-integer value. Okay? Because, we're working on this interval. It's just easier for us to take mod 1 because that's the point that we care about. And so we're going to arrive at a lot of those groups, like square 3 plus q mod 1 and blah blah blah. And so what we can show is that we have all those real numbers. Real numbers are not countable. That means that their infinity is bigger than infinity of natural numbers. Remember what we talked about a few minutes ago, right? Okay, great. So there are a lot of real numbers, and they are all divided into this classes. Okay? And in these classes, you have elements, and the number of those elements is just as big as number of rational numbers, right? Because all rational numbers that lie in the interval 0, 1, blah blah blah, they are countable, and we showed it, right? Okay, and so because you have countably many elements in each of the equivalent classes, and you have uncountably many elements overall, it gives me the conclusion that the number of those classes is uncountable. Long story short, you have fucking lot of elements overall. You have little numbers of elements in each group. It means you have fucking lot of groups. Okay? Make sense? Makes sense. Okay, means we have uncountably many classes. Fucking lot of groups. Great. So, what we're gonna do is we're gonna see some observed properties. It's clear to you that this class and this class are just shifted versions of one another. If I just add plus square root of 3 to this class, I'll get this class. Yeah? Yeah? Okay. If I add plus square root of 2 to this class, I get this class. Right? So basically, they're just shifts of one another. If they are shifts of one another, that means that they have same number of elements in each of the groups. Right? Same number of elements. Okay, great. And number of elements that are points for us mean that they have same measures. That would be very important for us. Okay. And so basically, if we have this property and disjoint because they are shift versions of one another. Like, there is no way that square 3 plus a rational number would be equal to any rational number, right? Okay, and we actually can show all that, and I have that in my notes, but like, those proofs are quite easy. They're just some like equalities, you like subtract stuff, and they are very easy. You can just like read them if you want to, but I just didn't want to like spend time doing that because that's not interesting. Okay, so there is disjoint. That means if we're gonna sum them up, we're not gonna count the same element twice. That's what matters. Like, because if you know, if you do a summation of two sets and you have some set in the middle, you just count this element twice. We don't want to do that. We want it to be disjoint. Okay, great. So now we can just show why Finality sets are non-Lebesgue measurable. Okay, so we took all those classes, right? Now let's just take one element from each of those classes. What does it look like? Looks like an axiom of choice. Because we have infinitely many classes, and we're taking one element out of each class. Okay, and that means that we're doing axiom of choice. So, danger. We are using axiom of choice. Okay, and if we're able to construct a set that includes one element out of each of those sets, we'll have a Finality set. Okay, great. So basically, we would be able to show that Finality sets are disjoint and that they have some number of elements. Okay, I mean, those you can just check out. Okay, we got these two properties. What happens next is just very simple. Let's assume that Finality set has measure. Okay, let me just erase something out. Okay, let's just assume that Finality sets are Lebesgue measurable. Okay, we assume that they all have the same number of elements, means they are having the same measures. They are all disjoint, and we have uncountably many of them. So basically what it means is that if we put all of Finality sets together, they'll make up all points on our interval from 0 to 1, if we just like put all their elements together. So, and each of them has some measure, right? So if we just add up all of their measures, we're gonna have a measure 1, right? Because all of their elements are just making up points on interval 0, 1, right? So if we just put them all together, all their measures is 1. Is that understandable? Great, okay. They all have the same measure, and there's uncountably many of them. So imagine that their measure is equal to 0. Like, measure of Finality set is equal to 0. Great. Then sum of all of the Finality sets is equal to 0. But then the length of this interval would be equal to 0. So we know it's 1, right? Okay, that means that it's just not 0. Okay, let's try something else. Let's just say it's x, and x is not equal to 0. Then sum of infinitely many x's, whatever that x is infinity. And the sum of it is just infinity. But our length is still 1. That means that this also cannot be a measure of Finality set. That means there's just no measure. Finality sets are not Lebesgue measurable. Is it clear? I mean, if you don't have the whole proof, what actually was needed is like, we take sets from classes, from the sets we make binary sets. Binary sets have the same number of elements. If you add up all of their elements, they make integral 1. If you add up their measures, they either make 0 or infinity. They cannot make up interval with length 1. Okay? Okay. It's something like, I mean, it took me 3 weeks to get this proof. Because I'm very slow, you know. But if you see the general picture, looking at like details of the proof would not be too hard, because like the proof is not too hard. Like you can understand it. I mean, I know you can understand it. Okay, so just relax, because we don't need that anymore. What we did, and we did the first arrow in our proof line. So we said this: we had an axiom of choice, and we were using it when we were constructing binary sets. That means that binary sets have to use axiom of choice. And also, they are not Lebesgue measurable. Okay. And what we are gonna do later is globally, we're gonna say we have axiom of determinacy. And with it, we'll be able to show that all sets are Lebesgue measurable. Okay, pause for a second. What does it tell you about axiom of determinacy and axiom of choice? Axiom of choice help us to construct binary sets. Binary sets are not Lebesgue measurable. Axiom of determinacy help us to show that all sets are Lebesgue measurable. What does it tell you about this axiom and this axiom? If they help us to reach totally different conclusions. Like this conclusion is totally opposite to this conclusion. It means that these two axioms are actually contradicting each other. They cannot exist together. Like if you put them in one set theory, that's not a very good set theory. Okay, so that means if you're gonna make up axioms for your set theory, don't put them together. That's a very bad decision. Because they lead to contradicting conclusions, right? Like you cannot have sets that are all Lebesgue measurable, and then there are some that are still not Lebesgue measurable. So that's clear, right? Okay, great. So that is like a grand picture of what we were doing. Like on this lecture, what we're doing is basically this. And we were planning that on the next lecture, we're gonna do this. But I'm not sure if we're gonna continue. I mean, that would depend on your feedback. Like, would you want me to show you with help of infinite games that this leads to this? Because I can show you today only the first half of it, because I don't have time for another half of it anyway. But like, I'll be happy to show it if you want. Okay, guys, please put your hands up if you want me to show half of this. One?
Not
two,
sure.
Oh?
Not sure.
Not sure? Okay. Do you find this topic at least mind-blowing? Because my aim was to make it mind-blowing, you know, like this is real math. If you see that your calculus lesson is math,